Hello, and welcome to the third and last lecture on the series on random variables and probability distributions. In the first lecture, we introduced the concept of random variables, spoke about how probability distributions can be discrete or continuous, and we also introduced the idea of PDFs and CDFs, probability density functions and cumulative density functions. In the second lecture, we targeted about 5 or 6 distributions, commonly used distributions, and we introduced them, as well as talking a little bit about how one can get the CDF if you're given the PDF. What is the relationship between PDF and CDF, and vice versa? How do you get to the PDF given a CDF symbolically? And we also spoke about how you can mathematically, given a distribution, compute its mean, compute its variance, and so on. In this lecture, we're going to focus more on a single distribution called the normal distribution. Many of you might have already heard of it. But we're also going to look at some applications associated with this distribution. And one really important application has to do with inferential statistics, which is something that will be quite central to the next 4 or 5 lectures. So it's in that idea that we're introducing the normal distribution. Great. So the normal distribution itself, you might have come across it. If you've not, you might have heard of this thing called the bell-shaped curve. So the distribution itself looks like the shape of a bell. So just like the uniform looks like a flat line, and different distributions have different shapes, this looks like a symmetric bell-shaped curve. And the probability density function of this distribution is characterized by this formula, the formula that's shown here. And one thing that's noteworthy is that this distribution has 2 parameters, mu and sigma. So the distribution itself is defined by the mean and variance. So the mean and variance of this distribution go into that formula and they define it. So there's no point saying, tell me what is the probability of value x for a normal distribution, because that question does not make sense. You'll have to say, for a distribution with this mean, with this variance, what is the probability of a value equal to or greater than x? So that question means more. What is the probability of finding a value between x and x plus delta for a normal distribution with a mean mu and a sigma equal to sigma, and a standard deviation equal to sigma. But once you're given the mean and sigma, it's quite simply this formula that you would use, and you can compute the probabilities. So what is the mean of a particular normal distribution defined by a mu and sigma? Well, that's very straightforward. It is the mu, because the distribution is defined by mu, and the variance is nothing but your sigma square, right? So you can it's quite straightforward there as well. The CDF, however, is not something that simplifies very elegantly. So to define the CDF, you would still use your traditional procedure of using the integral, and by the way, the normal distribution goes from minus infinity to plus infinity, so it makes sense to actually use the minus infinity here. So you would actually use the minus infinity to x, f of x, which is the PDF, which is nothing but this formula, right? So dot dx, right? But while in many distributions this whole thing simplifies and you're able to do that integration and there's an actual value, with a normal distribution it does not simplify very elegantly without using more complex algebraic terminology. So the CDF is often just stored in tables sometimes, especially for the normal with mean 0 and standard deviation 1, or it's just something that you integrate each time to get. Now this is a very interesting distribution because there are a lot of things that are normally distributed. So things like people's height, weight, well, height obviously within each gender, grades in a class, marks that people score in exams. The core idea with the normal distribution is that unlike the uniform distribution, which says everything is equally likely, it's the normal distribution says that things in the extremes are less likely, things in the center are more likely within certain limits, which is what gives it its characteristics bell-shaped curve. I mean, if this is any attempt at a bell-shaped curve, we're basically saying that things that are on the extremes, like here and here, are less likely, and things in the center, like here, are more likely. That's why they have a greater height, right? With all of these things, the y-axis is the probability. So if you take a look at something like heights, or let's say weights, and you fix a gender, let's say male, and you take something like people who are registered for Introduction to Data Analytics course, then you will find that there might be very few people who weigh less than, I don't know, 40 kgs or 50 kgs, men especially, and you will find very few of them probably weighing more than 100 kgs or so, and so that kind of tapers off. On either extreme you find less, in the center you find more. But there are many other distributions that are also like this, but that's a key feature of being on that bell-shaped curve. The other thing is, many things after you remove outliers start to look normal, and we'll talk about an example of that. In this slide, I'm just going to talk about the other things that we will talk about in this lecture, so I'm not kind of rushing through it. We will especially take up from here and till here and go through them in detail with slides. But you'll also encounter that there is this thing called the binomial approximation, which is, and we briefly spoke about this when we introduced the binomial distribution, that certain problems which just by definition look like they fall so cleanly as a binomial distribution, for computational reasons could be quite easily approximated to a normal distribution, although the binomial is a discrete distribution and the normal is a continuous distribution. We'll also talk about something called the central limit theorem, which makes the normal distribution very useful for many applications, and also a very interesting concept per se. And finally, we will look at the idea of sampling distributions. The core idea being that if you take a random sample of size x, associated with any variable, so I randomly select 5 people and measure their heights, is there a distribution associated with the parameters that I get, like the mean and standard deviation? But we'll talk about this in greater detail. So the first thing is things after removal of outliers. Right? So here's an example of some real data where we looked at the total annual household income, and so the graph that you see to the left hand side is it's essentially all these households with income up to we've just stopped the x-axis at a certain point. And so we said let's look at income up to a certain value, and the y-axis is the number of households. So I've created essentially a histogram, but that's a proxy for finding the probability distribution itself. So you can think of the probability distribution as something that looks like this, right? In this particular case, people can't have incomes less than 0, so on and so forth. Now look at the same graph where I said I'm not going to look up to 4 lakh rupees income, but I'm just going to concatenate the x-axis at 90,000 rupees. So the whole idea was to say that some of these values could have been outliers, and we took a certain value beyond which we go. And already you can see that this graph is starting to look a lot more bell-shape-esque. Probably not perfect, but the core idea is this, which is that sometimes once, even though the distribution originally might not look normal, with sufficient amount of outlier removal, the distribution could truly be normal. The second concept that we want to speak with respect to this is the binomial approximation, right? So let's just very quickly review what the binomial distribution was about. We spoke about how this term in the PDF of the binomial distribution was really n choose k, so n combinations, k combinations out of n was the core idea. And that's fine, right? So if you have problems of the type saying what is the probability of finding, you know, 3 heads out of 10 tosses, this works fine. You can substitute the values, get the PDFs. Now if somebody came and asked you saying what is the probability of getting 2100 heads out of 5000 tosses, right? Then you essentially need to, if you want to use this formula, you need to plug in 5000, C 2100 or whatever the number is, and that's a very large number. It's a very hard computation, and you could 5000 and 2100 is just an example. That could be 5 million and um, 200,000, and it's very hard to do those calculations. So one thing that you can do when n becomes really large is you can essentially use this formula that you have for mean and variance of the binomial distribution, um, and construct a normal distribution with this mean and this variance, and use it to answer distribution related questions. So you, for instance, if there's a 50% chance, for instance, of a coin falling heads or tails, you can say, well, the mean for 5000 tosses, right, is 2500, because you have 5000 tosses times 50% probability, so that's 2500, and that's your mean. And your variance also you'd similarly calculate by plugging in n equals 5000 and p equals 0.5. And once you do that, you can essentially construct a normal distribution with these parameters, and you can answer questions like what's the probability of there being more than 2100 heads, or what is the probability that the number of heads will be between 2000 and 2500 out of 5000 tosses. You obviously can't answer a question like what is the exact probability of getting 2112 heads, because you've essentially converted this to a continuous distribution. And the idea of answering a question like what is the exact probability of 2121 tosses out of 5000, 2121 heads out of 5000 tosses becomes relatively meaningless, because as n keeps becoming large, the probability of any one thing exactly occurring becomes really small, becoming close to zero. So you're interested more in intervals, which is in spirit what you can do with continuous distributions, and you can use the normal approximation of the binomial distribution to achieve that, as long as n is fairly large. Okay. Next we'll move to something called the central limit theorem, and the core idea here is that the aggregation of a sufficiently large number of independent random variables results in a random variable which will be approximately normal. Okay. So what does that mean? It just means that, look, if you have some process and it's some distribution from that process, so let's say flipping a coin or throwing a dice is the process. Now central limit theorem says as long as I'm aggregating many such processes, so if I said, instead of asking you the simple question of the distribution associated with what I would get if I roll the dice once, right, I instead say I want to know the distribution associated with rolling the dice twice, and I'm going to add them up. So the first time I'll roll the dice, right, and then I'll get some number, I'll write it down. I'll roll the dice another time and I'll get another number, and I'm going to add those two numbers up. Now the distribution associated with that sum is also a probability distribution, right, because it's still a random process. There's still some chance that I can get each value. I clearly cannot get any value less than 2, because first time I can roll 1, second time I can roll 1, so I can't get 1. I can only get 2 as the minimum value, and the maximum value is 12. I can roll 6 and 6, and that's 12. Right. So the idea that is being put forth here with central limit theorem is that aggregating it, and the word aggregating can be thought of as taking the sum, or you can think of it as taking the average. Both are forms of both are essentially the same thing. The difference between sum and average is just divided by the number of times, but this form of aggregation of a sufficiently large number of random variables results in a random variable which will be approximately normal. So let's see how that works, right? So on the left hand side of graph out here, I talk about the distribution associated with a single role, right? And this we've seen and we've discussed, this is uniformly distributed. Why? Because the heights are all in the same. It's a discrete distribution and it's a uniform distribution, and it's 1 by 6, right? That's what I've shown out here. Great. On the right hand side, I show you the distribution of the sum of two rolls. So you can think of it as rolling it once, writing it down, rolling it second time. So you can think of your hands having, two dice, and you roll both of them, and you sum up what you see, what shows up. And already you can see that the distribution has started moving from uniform to something else. This happens to be triangular, but that's just the first step towards starting to look more and more bell-shape-esque. Right? What's happening now? Although the probabilities of rolling 1 through 6 were uniform, right? The summations, however, are not equal. So the probability of getting a 2 is lower than the probability of getting a 3. Right? And that should be fairly intuitive, right? For you to get a 2, you need to roll a 1 the first time and roll a 1 the second time. Okay? But there are many ways in which you can get 3, mainly 2. You can roll a 1 the first time and then roll a 2, or you can roll a 2 and then roll a 1. And that kind of keeps increasing till you hit the point at 7. Right, where 7 you can get in so many ways. You can roll a 6 the first time and then roll a 1 the second, or if you're thinking of rolling both at the same time, you can get a 6 and a 1 and a 6, a 3 and a 4 and a 3, a 2 and a 5. So there are more ways of achieving the same thing, of achieving a 7. There are fewer ways of achieving a 2 or a 3, and so you already have something that's looking more like a normal. Now you go further, right? As I discussed, obviously the average of two dice is the same as the sum of two dice, right? So these two graphs are identical. This one and the next one on the next slide, these two are identical, except that I've changed it to average, and so this axis is different. It goes through 1 through 6. The other one went from 2 to 12. Right? But these are essentially identical graphs, and this is also a triangular distribution. But look at what's already happening. Now if I say the average of 3 dice, so I'm going to roll 3 dice at the same time, or I'm going to roll one after the other. They're all independent either way. What you're going to see is that now this has started looking a little bit more, triangular. It's starting to get that little bit of inflection and so on. And so as you increase this number more and more, the idea is that you get something that looks fairly normal. And that's what the central limit theorem is about, that you aggregate a sufficiently large number of distributions and you start getting a normal distribution. Now this is a really important point for what we're going to say next, associated with sampling distributions. So we're going to start afresh on sampling distributions, but I just want you to keep in mind what we've discussed now in central limit theorem. Okay, so jumping gears now to sampling distributions. The idea here is fairly simple. Okay, so you have some original distribution, and let's for now say this distribution is normally distributed. Okay, and let's say this normal distribution has some mean, which I've shown with this blue vertical line, and let's call that mu. Okay, so this point is mu, and let's say it has some standard deviation. Right? I'm just referring to the dispersion through the arrow. That's not the exact length of the standard deviation, but it has some standard deviation which can be represented as the variance is represented as sigma square. And by the way, this n mu comma sigma square is fairly nomenclature. That just means it's a normal distribution with that looks like a with mu and sigma square, although that looks like an m. Okay, so maybe a little bit more like mu now. Okay, so you have this distribution. Now let's say and let's give it a name, right? So let's say this is the distribution of heights. This is the distribution of what do we okay, let's keep weights. So this is the distribution of weights, staying consistent with the previous example of the men or the male members who've registered for introduction to data analytics. So maybe this distribution starts somewhere at, I don't know, 50 kgs and goes all the way to say 100 kgs. This is the distribution. Technically it can go all the way to infinity, because by definition a normal distribution can go to infinity, and on this side it can go to minus infinity. Okay, so this is the normal distribution. Now let's say that I took a sample from this distribution. Okay, so these data points, right, these data points represent the different samples, and in this particular case I've taken just 6 samples, right, but that can be more, and the heights mean nothing. The samples just mean where they fall in the distribution. You can obviously use that and build a histogram, and the idea is that if you take a sample large enough, that histogram will fit very neatly to this curve, which is the normal distribution, if that sample is very large. If the sample is not, you might get a different histogram. But what we are most interested in is taking this sample and computing some key statistics from the sample. For instance, if you took the sample and computed the arithmetic mean of the sample, so you'll take each data point, right, and let's say you call it x1, and the next data point got called x2, and so on. Then what you're looking at is x1 plus x2 plus dot 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 divided by n. That's your arithmetic mean. And so you compute an arithmetic mean, but since you've got some finite sample, you've got like 6 points, and maybe you have in another instance 10 points, the question is, will your arithmetic mean always be equal to mu? Remember, mu was what defined this distribution. So this distribution is by definition mu comma normal mu comma sigma square. But if you take a sample, if you take some x's and compute x bar, we differentiate between mu and x bar, meaning mu is a theoretical mean, whereas x bar is the sample mean. It's if you take a sample of size n and compute an x bar, will this x bar be equal to mu? And both intuitively and otherwise the answer is no, right? Theoretically, if your sample size is equal to infinity, that means you take infinite number of samples, then perhaps your sample mean will be equal to then your sample mean, again in theory, will be equal to mu. But that's not a practical situation. Who takes infinite samples? Like that by definition does not make, it's not very useful. So if you take a finite sample, and in this case 6, in another case it can be 20, let's say 20, and you compute a sample mean, it's not going to be equal to mu. But the idea is that it's also a random variable. What do we mean by that? We mean that, one time you go about, you take a sample of 10, let's say, and you take the mean of that sample, you'll get a particular value. That won't be equal to mu. It could be equal to mu, but it could be little less than mu, little greater than mu. Now you go do that exact same thing again, right? You'll get some other new value. So what that means is you have a random variable on your hands, and the random variable is about the distribution of the sample means for a given size n. So that's a core idea associated with sampling, which is that from the original distribution you take a sample and you compute a mean, you get a certain value, but that value itself belongs to a distribution. That distribution changes based on the sample size. So suppose we were, like I said, if you took infinite, if your sample size was really large, if it was infinite, then perhaps you won't even have a distribution, you'll just have a line out here, which is that you almost always get mu because your sample size is so large. But if you but think of the other extreme. Suppose your sample size was equal to 1. That is, each time you took 1 point from the distribution, right, and you computed the mean of that point. What does it mean to compute the mean of a single point? It's that number itself. So let's say we were looking at 50 kgs to 100 kgs. You took a random sample of 1, so 65, 65 kgs this time. That was a random number I picked. The average of 65 is 65. Okay, so if you had a sample size of 1, what would the distribution of sample means look like? The answer is it would look exactly like this distribution, right? Because you're taking a sample size of 1. It's essentially like, and you're computing the average of that, which is nothing but that number itself. So it's essentially like just replotting that graph. Now, if your sample size was greater than 1 but less than infinity, right? What happens is, if your sample size, as the sample size gets larger and larger, you're dealing with a distribution still, because each time you take a sample of, let's say, 5 or 10 or 20, you're going to get some sample mean from that, and that sample mean is not going to always be equal to the exact overall population mean, but it's going to be some number nearby. And the idea is that, as in this particular case we had a normal distribution, and the idea is that as long as you're taking the average of some number, let's say 10 or 20 or 30 or 40 or 50 samples, you are going to get a mean. But that mean is not certain. It's not certain what that mean is going to be. It need not be mu. You know that for a fact. So what you're essentially getting is another distribution. You're getting a random number from another distribution, and this is the distribution of the sample means. Now it so happens that when your original distribution is normally distributed, the distribution of sample means is also normally distributed, but there might be some questions you have in this regard, right? So for instance, what is the shape of this distribution? The quick answer to that question is, when the original distribution is normal, like we said, this distribution of sample means is also normal. But we also went through the central limit theorem, where we said as long as you're aggregating a sufficiently large number of distributions, the resulting distribution starts to look normal. So even if your original distribution is not normal, right, as long as you're aggregating a sufficiently large number, this distribution of sample means, right, becomes normal. Okay, so that's the shape. Now what's the mean of this distribution? What is the mean of the distribution of sample means? The quick answer is, because you're just taking the average of some numbers, if you were to do this a sufficiently large number of times, you should not get a mean that is biased. So the mean of this distribution will also be equal to mu. But it's clear that the standard deviations are not the same, right? The standard deviation would be the same if your sample size was 1, in which case you're not really sampling, you're just taking a single data point. But depending on the size of the sample, the standard deviation is going to be typically lower, right? It will always be lower as long as the sample size is greater than 1. And the relationship is nothing but sigma square. So if you're using sigma square, it would be sigma square divided by n. I'm going to use small n to refer to the sample size. But you can also think of it as taking the square root of this. You can also think of it as sigma divided by square root of n. So this would be the standard deviation, and this would be the variance. So this is V A R. This is the variance, and this is your standard deviation. Okay, so that's a relationship that's very useful to remember. Now you might have a question saying, okay, so we did all of this work to say that you have an original distribution, you randomly sample from the distribution, and you compute a mean, an arithmetic mean, then that arithmetic mean that you compute has a distribution of its own, and we spoke about the mean and shape and standard deviation of it. Similarly, if you take a sample from the original distribution and you compute a standard deviation of that sample, then is that sample standard deviation also coming from a distribution? And the quick answer to that question is yes. And if you're using a normal distribution to start with, that distribution of the sample standard deviations tends to be chi-square distributed, and that's also something that we will encounter. But our focus for now has been on the distribution of sample means, and the important things to take away are, if you start with an original normal distribution, then by theory you will have a normal distribution for your sample means for whatever sample size. But given that we've also learned about the central limit theorem, even if you start with an original distribution that is not normal, as long as you aggregate sufficiently large number of as long as your sample size is large enough, then the distribution of sample means is likely to be normally distributed. We spoke about how the mean of the distribution of sample means should be no different from the mean of the original distribution, because you're not adding or subtracting any number, you're just taking average numbers, you're just taking numbers and taking the average of them. So if you do that many times, the distribution that you get from that should also be centered around the overall grand mean of the original distribution. We spoke about how the standard deviation, however, keeps reducing. Right? So as long as you're aggregating more numbers, your standard deviation will reduce, and the rate at which it reduces is as a function of the square root of n, the sample size. So sigma divided by square root of n is the rate at which the your standard deviation of the distribution of sample means is with respect to the original distribution. And actually that phenomena you should be able to see even in the examples that we took with the central limit theorem. Just to kind of show that to you again, see in this particular example, and I'll erase the red mark. Okay, so in this particular example I was focusing more on showing you central limit theorem about how the shape changes, right? But if you take this graph, which is this uniform distribution out here, and there is some standard deviation out here, right? There's some spread around the mean, correct? There's some spread. Now take a look at the average of two dice, right? The mean is the same, it's centered around the 3.5, but the spread has decreased, right? Before, the spread was like this. So there was a higher probability of seeing values in the earlier graph, right, out here. You had data points that were with a higher probability further away from the center at 3.5. Now you don't see the probability of finding points far away from the center has reduced. These are low probabilities, but the probability of finding things close to the center has increased, right? So therefore the standard deviation of this distribution is lower than the standard deviation of the uniform distribution, and that effect is going to just increase. The probability of extremes keeps becoming lower, thereby the standard deviation becomes lower, given that for all of these you're starting with 1 and ending at 6. Okay, so that example shows both the central limit theorem, meaning the change in the shape, but you can also capture this idea, which is the distribution associated with sample means. And in the previous cases, the sample size was 2 in the first example, and the sample size was 3, right? Because we were averaging 2 dice or 3 dice, right? So the distribution that results from that is having a lower standard deviation. Okay, so that should give you an idea of the whole idea behind sampling distributions, and this is a good concept to revise or understand deeply, because a lot of inferential statistics is based off of this. And with that, we conclude our lectures on random variables and probability distributions. We will continue our next class and focus more on inferential statistics.